Okay, so I'm going to explain a very simple linear program formulation. This is the transportation problem, and it's something that's very common in logistics. So let me just read the prompt. It says, consider the following scenario. There are n warehouses, each with a supply given by Si, for all I such that I belongs to the set including 1, 2, 3, up to n. And there are also n retailers, each of which has a demand of dj, right? And then again, j ranges from 1 up to m. Provided the information about the costs of traveling between all pairs of warehouses and retailers, formulate a linear program to find the plan of action with minimum cost. So the way I typically tackle this problem is by just making a digraph drawing, I guess you could call it. Essentially, on one side, you draw the set of locations representing the warehouses, and typically I just write the first couple dot 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 up to n, correct? This represents the set of locations of warehouses, right? I can call that I, or yeah, I can call that I. And then on the other hand, we have the set of retailers, right? These represent the actual clients. And I would typically just write the first couple, like before, up to M, right? N and M don't have to be the same. I draw 3 points here on each side, but of course, like N is not necessarily equal to M. And this I just named J for convenience. Make sense? Then what I represent next is all the possible connections, right? For example, in warehouse 1, I have S1 as my stock. That's how much material, how many products I have stored in that warehouse. The same for 2 and up to n. And what I'm trying to say is that from S1, you're allowed to send your product to any of the retailers, right? There could be, you could send products in this direction. You could also send them in the other direction. You could send it in both directions. What I'm trying to say is that this is a complete bipartite graph. There's an arch between each node in each of these two sets. I don't know if that was clear. Okay, so if I pick a node in set I and a node in set J, there's always going to be an arch between them. I guess maybe that's a little more clear. But anyway, let me just draw a few more just to be clear. And of course, even though I only drew 2 here, this keeps on going. There are many, many, many of them, right? And the same for n, right? There could be some going out for each of the retailers. So all in all, now that you've finally drawn all the arches, the thing that I typically do is just represent all the costs. And for that, I can just define a new parameter. It wasn't given on the actual, so we're given the supplies, so we're given the demands at each retailer, and something that we're not given is the actual costs per unit sent along an arch. And typically I just call it Cij, right? That represents, I can just say the cost of sending 1 unit from from warehouse I to retailer J, right? And obviously this parameter will be defined for all I in the set I and for all J in the set M. So you should expect there would be n times m cost values, and they might be different, they might be the same, we don't know, but it doesn't matter, right? Because this is all symbolic, right? So basically, we have the big picture. This is the big picture of the problem. right? We have knowledge of all the parameters now, and now we can actually start our formulation. So let me just scroll down a little bit. I have a formulation, and in this case, it's going to be an LP formulation, correct? The way I always start is by defining the decision variables. These are the things, the specific variables that our program is going to have to vary, right? It's going to change the values for these variables and find the optimal values that these variables have to take in order to minimize the cost of satisfying all the demands, right? So maybe I hope that's clear. In this case, really, if I told you to represent the plan of action, I think it's clear that you would only need to tell me how much you are sending from each of the warehouses to each of the retailers, right? The variable that I usually utilize for these is xij. In this case, xij would represent how much I'm sending, how many units, right? This can be product, how many units I'm sending from warehouse I is the same as before to retailer. And yes, I mean the indices are the same, but these two symbols are different. This one is given to us. We know that before the start, at the start, whereas this one is just a variable that we've created and that we have the ability to modify to find the optimal, right? Yes. Something else that we should say is that this variable is always going to be greater than 0, right? Because you cannot send a negative number of units from one from the warehouse to the retailer, right? But I think we can write that on the constraints. For now, I think, are we done with decision variables? This is how many units I'm sending, and I think that's it, because there's nothing else we have to keep track of, right? So we can just go ahead and move on to constraints. Or should we maybe we'll do the objective function first. Now that we finally defined the decision variables, maybe it's a good time to tell the program what it is that we want to achieve, right? This is our objective. And in this case, we have it written at the top. It's like we have to minimize cost, right? Of course, we have to satisfy some conditions, like the cost cannot just be 0, right? Because you still have to satisfy all the demands. But we're gonna specify those conditions on the constraints. For now, we just have to say that we want to minimize the sum of the costs, right? And when I say the sum, I mean the sum of the cost of sending stuff along this arch and along this other arch and so on. So I would do the sum of all xij times cij, right? Basically, I don't know if this is clear. Yes, where I ranges from 1 to n and j ranges from 1 to m. Right? This is what we want to minimize. Let's say, for example, like if I told you that I want to send 2 units along this very first arch and 2 units along this one, 0 along everything else. Well, clearly you would just need to tell me like the total cost would just be 2 units times whatever the cost is between these two nodes, would be 2 times C11, right? And then it would be 2 times 1 times C1m, right? Like basically, if you expanded this, like typically we don't do this, but just to be very clear, I don't know if this is confusing for people. You would expand it this way. You'd have how much you're sending along the very first arch, right? From one to one, right? If it and then if I'm sending 1 or 2, I don't know how many I'm sending, but whatever it is, I'm going to multiply times the cost per unit, right? Along 1, 1. Then I would do the same thing for the next arch, 1, 2. X1, 2 times C1, 2, and so on. I would do that for all the possible arches between 1 and each of the retailers, up to 1M times C1M, right? Yes. Then you would move on, you would keep going for the next one, and you would do X2, 1. That would be this arch from 2 to 1, 2 to 2, and so on. And the approach would be very similar. 2, 2, the cost of 2, 2, and then up to the very last, to M. And you could just keep going and do it for every single one of the warehouses, right? Then you do from N to 1, N to 2, and so on. So I know this was a little digression, but I mean, you can always skip if this is too easy, right? So N to M, and C N to M, right? So this whole summation is what I'm capturing in my objective value, and that's what I want to minimize, okay? But of course, like if I just gave this to the optimizer, then the optimizer would just make all these variables equal to 0, right? It wouldn't send anything from along any of these arches, right? And the objective function would be 0. It would be completely minimized. But of course, we don't want that. We want to actually satisfy the demands, right? And of course, we don't want to like send more than we have. At a specific warehouse, we don't want to send out more than we originally have in that warehouse, right? So we need to write constraints for those things. And I'm going to do that now. Constraints. There we go. And basically there are two main constraints, right? First one would be satisfy the demands. Essentially what this means is that if I pick any of these retailers, right, which are the end consumers, the clients, I want to make sure that however, like if I sum everything coming into this node, it has to add up to at least dm. Make sense? So the way I do that is the following. I first identify what these, so like 2, for example, let's focus on this one. You'd see all the arches coming into 2, right? This would be, how much is it coming from 1? It would be x1, 2. How much is it coming from 2? It's x2, 2. And so on out to n, and it would be xn2. If I sum all of those like incoming arches, I would find out how much in total is coming into 2. And I would need that total to be at least d2, right? So I would write that as follows. I would do the summation of xij. I know I said 2, but we have to generalize it for all possible retailers. So I'm just gonna do j for now, right? But notice that I'm only adding along the suppliers. So I'm adding across I. It would be from I up to n, because we have n suppliers. I'm adding everything that goes into j, right? And that has to be at least, so greater than or equal to this demand that, the demand the retailer J has, right? In this case, you could replace J with 2, and we go back to the example that I discussed earlier, right? The only thing that we need to generalize is that this should apply for all j in the set of retailers, right? All j belong to M, right? So there you go. That's the first constraint, arguably one of the most important ones. And then we have another constraint, right? Because we also have to take into account that we don't have an unlimited number of units on each of the warehouses, right? So we need to make sure that we control how much we're sending out. Like if the first warehouse only has S1, everything going out has to be at most S1, right? If I only have 10 units, I would not be able to send 11 out, right? So that's actually a very similar constraint. What should I call it? Supply constraint? Yeah. And essentially what we would do is add everything going out from node I, right? Let's say I is 1. Then you'd add up x 1, 1, x1, 2, x1, 3, x so on, x1m, right? And that you should expect to be less than or equal to the supply in that specific in that specific warehouse. Again, you would do that instead of just for warehouse 1, you would do it for all the different warehouses, right? And you would be able to find the optimal solution. One last thing would be, actually, I almost forgot about this. Yeah, just in case. Sometimes this is necessary, sometimes it's not, but it's always more correct if you write it down, right? We need to make sure that xij is greater than or equal to 0. That's what I said earlier. We cannot send out any negative amount of units. And of course, this is for all I and all j, right? Okay, so I think that's it. I don't know, maybe I'll make more examples in the future.